Hi, I'm Alistair, and in this video I'm going to show how you can convert any regular telephone into an audio guestbook. So you could have this at a wedding reception or at a party, and when guests pick up the handset, the first thing they hear is your recorded message.
Hi, this is Alistair. Again, please leave your message after the tone.
And then it automatically starts recording everything said into the microphone for as long as the handset is held. When you've finished recording your message, you simply replace the handset back onto the base to end the call. Now, every time the handset is lifted, a new recording is made, and these are saved as numbered audio files onto an SD card, which you can remove, put in your computer and listen to the messages, or save them as MP3 files, whatever you want. And the audio is saved as 16-bit 44 kHz CD quality recordings. Now, I've also put a button onto the back of the phone that will let you review the messages currently on the card by playing them through the earpiece of the handset itself.
And then it automatically starts recording everything said into the microphone for as long as the handset is held. When you've finished recording your message, you simply replace the handset back onto the base to end the call.
Now, I've seen a couple of companies that hire these kind of telephones out, but with a little bit of coding and electronics, it's actually pretty straightforward to build your own, and I'm going to show you how. You can buy all of the components required for around £30. Okay, so you are going to need a telephone. Here's one I picked up off eBay. It's a GPO Model 746, which was an incredibly popular telephone handset here in the UK throughout the 1970s and 80s. It is solid and robust, and it's very iconic. One of the nice things about building your own audio guestbook is that you can choose a telephone handset style that matches your theme. So we need to identify a few parts that we need to get to work for this project. We need the microphone and also the speaker in the handset. And we also need the hook switch to detect when the handset has been lifted and replaced back on the base. So if we open the telephone handset up, let's take a look inside. Now, most of the components here we don't need. They relate to the bell ringers or to the dialing mechanism. But if we take a look at this cable that's coming in from the handset, we can see that there are 4 coloured wires. There's white, blue, green and red. So how do we know what those are for? Well, if we actually take a look in the handset itself, we can unscrew the earpiece here. And inside we can see we've got the speaker, and that is wired to the red and green cable here. If I just place that back on, and then we do the same with the microphone end. And inside the microphone we'll find that we have the white and blue wire here. So that's the pair that drive the microphone. Now, I can't promise that the wire colours will be the same in your telephone, but it's pretty easy to find out. There will be a pair for each component, and you can simply trace them all the way down the cable to the point where they enter into the base here. And conveniently, in old-fashioned telephones like this one, those cables are then wired to screw terminals, which is going to make it very easy to connect to them in a moment. Okay, so what about the hook switch? Well, if I lift the handset up just to show you the mechanics of that a bit clearer. So when the handset is replaced on the base, it pushes this linkage down here through this spring mechanism and to this switch at the bottom here. So what we need to do is to find out which of the terminals here relate to that switch. Now, to find that out, I'm going to use a multimeter. So if I set this to resistance mode, and I'm going to take the probes and just connect them to different parts of the board. So I'll place that there so you can see the output. So if I touch this on different points here, when it reads 1, that means that the points I'm touching are not connected at all. If it reads a value that's close to 0, that suggests that there is a direct connection between them. So what I'm looking for is a pair of terminals that are unconnected when the handset is off the hook, but then become connected when the handset is replaced, because that means that these terminals must be wired either side of that switch. And in this particular handset here, if I place my probes on these 2 points here, you can see that the display reads 1 currently. If I press the hook switch down, that goes down to 0, and as I release it, it goes back to 1 again. So in this particular handset, that is those 2 points here. Now, if you don't have a multimeter, you could make a simple circuit with an LED and find out which pins make and break that circuit. Or you could also remove the board here and actually take a look at the traces on the underneath of the board to find out which ones go to either side of that switch. So whichever way you choose to do that, we've identified actually all the things we need. We've got the pair of terminals that go to the microphone, the pair of terminals that go to the speaker, and the pair of terminals that go either side of the hook switch. And that's all you need to identify in any telephone handset. And just to demonstrate that process again, let me show you another telephone handset. This time it's a much more modern design, but the principle is still exactly the same. So if we open this up, we can see that once again we've got 4 wires coming in from the cable that goes to the handset through this RJ9 connector here. And if we actually open up the handset itself, we can see that we've got the red and green cables going to the speaker. And this time we've got the black and yellow leads going here to the microphone. And this is actually a pretty common colour convention that you might find inside these phones. Now, as for the hook switch, well, that's here. And it's a little bit more complicated than the other one. I think there was originally an LED that lights up on the button here. So we can see it's actually got a ribbon cable connected to the hook switch that goes to the PCB here. But once again, we can take our multimeter and we can find out the pair of wires that relate to the switch being depressed or not. And if I just touch my probes onto the 2 terminals on the outside here, what we can hopefully find is I'm currently getting a reading of 0, and as I press the connector down, that changes to 1. So it's actually the inverse way round from the other switch. This reads 0 when the phone is off the hook, and then it goes to 1 when it's reversed on the hook, but we can easily swap that around in the code later. Okay, great. So now that we've identified the connectors on the phone handset that we want to use, we need to wire them to a microcontroller to provide the logic and record the audio. Now, in many previous projects, I've used Arduino boards, sometimes ESP boards, but for this project, I'm going to use a Teensy board. Now, this is a Teensy 4.0. It's very similar to an Arduino. In fact, you can write code for it using the Arduino IDE, and you can upload that code and power the board from a USB connector here. And that means that you can run this project remotely using a USB power bank or battery pack. Now, the reason why I've chosen the Teensy board is that they're particularly good for processing audio signals. When you're recording audio, you want to be sure that your processor can maintain a steady sample rate. So for CD recording, that's 44.1 kilohertz, or taking 44,000 samples from the microphone every second. So the Teensy has a 600 megahertz ARM processor, and it's got an I2S interface, which is somewhat similar to SPI or I2C, which are used to connect sensors, but I2S is specifically for transferring digital sound data. And it has this audio shield adapter that allows you to easily connect microphones or headphone outputs, and we're going to use this shield to connect to those terminals we identified in the phone handset. Now, one practical thing I'll mention is that when you insert the Teensy onto the shield, which I will just demonstrate by doing that, you'll notice that you lose access to all of the pins on the Teensy itself. And we want to use some of those GPIO pins to detect when the hook switch is pressed or not. So what I've done is I've installed some double height headers here. So these have got male connectors which have gone down into the audio shield, and they also have female connectors that have risen up above the top of the board here. So that's going to let me wire into those connectors still, even when I've got it slotted onto the audio shield. So here's a quick wiring diagram first of all, just to illustrate how we'll have the components connected together. We've got the two cables from the speaker going into the headphone jack on the audio shield. We've got the two cables from the microphone going to the pins that are on the reverse of the audio shield here. And then I've got the button that will play back messages saved on the SD card. That's wired to ground and to GPIO pin 1. And the hook switch on the telephone is wired to ground and GPIO pin 0. And now I've not shown it here, but the USB connector here will be connected to a 5-volt power supply. And here's how I've got that physically connected within the handset itself. So we've got our screw terminals that we identified earlier, the pair for the microphone, the pair for the speaker, and the pair for the hook switch. And what I've done is I've screwed one more cable into each of those terminal connectors, and they are going down this bundle of wires here into this chock block connector. So this is simply a set of screw terminals, and it's a convenient way to be able to join wires from the Teensy here into the appropriate connectors on the telephone itself. Now, if you were trying to contain all of these electronics within the body of the telephone itself, what you might prefer to do is to solder those wires directly onto the board here. But I think for this particular project, what I'm going to do is I'm going to take the connector and the Teensy and also a 5-volt USB battery pack, which is what's going to power the Teensy here. And I'm going to place all of those in a standalone box that's just by the side of the telephone itself. So I don't mind the fact that the connector block has increased the footprint slightly. I think it's going to be worth it for the convenience of just going to be able to screw these connectors in to replace them, move around, and it actually generates a very good contact between those cables. That's very sturdy. So that's just a convenient way of connecting wires to know about. There's one more component I'm using here, which is this little breakout board here. So just to explain what this is for, the audio output from the Teensy we're using is the headphone out that's provided by this 3.5mm jack socket here. So what I've done is I've plugged a regular audio cable into that socket there. And what I could do now is to cut this cable here and take the wires from it and wire those directly to the wires that are going to the speaker output in the handset here. But the reason I like doing it via these breakout boards is because this is a sort of a totally non-destructive way of doing the wiring. The way that this breakout board here works is I've simply taken a regular 3.5mm jack cable here, and when you plug it in here, it provides 2.5mm pins for each of the sections of the audio data that are being transmitted. So these audio components here, depending on whether it's stereo or mono and whether it also includes a microphone input, you might get different numbers of bands on these cables. This, you can see we've got 3 bands. We've got the tip here and we've got 2 rings as well. Now we actually only need to use 2 sections of the cable here. So we're going to use the sleeve and the tip. So I'm just going to put this connector onto the end here, and this we will wire to the green and the red wires, which was what was going to the speaker in the handset here. The blue and white cables, well, they were going to the 2 pins that relate to the microphone input, and they are wired to the mic and ground pins on the bottom of the board here. And the black and white cables here Well, those were to the 2 side of the switch here, and those are wired to ground and to 0 on the top of the Teensy. Now, to program the Teensy board, we're going to install some software for it. So if you go to pjrc.com, who are the manufacturers of the Teensy board, and click through to Teensy, then TeensyDuino, and download and install, and choose the package that's appropriate for the operating system you're using. I'm on Windows, so I've clicked the Windows installer at the bottom here. Now, once that installer application is downloaded, you can run it and you'll get a dialog window like this. So if we just step through it, on the first page you get the option to install a USB serial driver. Now, if this is a machine that you've already used to program an Arduino or another similar microprocessor board, there's a very good chance that you'll already have that driver installed on your system, in which case there's nothing to do on this screen. Now on the next one, you need to specify where your Arduino IDE is currently installed on your machine, and it's going to install TeensyDuino into a subfolder of that directory. So on my particular machine here, I think this is the default location. It's in my program files directory, and then it's in the Arduino folder here. But if yours is saved somewhere else, you can just navigate it. It won't let you proceed to the next screen until you choose a directory in which the Arduino installation has been found. If you click the little question mark button here, you'll see it will actually tell you it's searching for all these supported versions, and if it finds one, it will actually report where it has found a valid file. So in this case, I'm building it against Arduino 1.8.16, and it's found the relevant files here, so it's going to let me proceed by clicking the next button. Now on this page, you can choose which of the optional Teensy libraries you want to install. For this particular project, the ones that we're going to need are the audio library, obviously, the bounce library, which we're going to use to debounce the button input and the hook sensor on the phone, and also the time library, which we're going to use to add a timestamp to the recordings as we save them on the SD card. If you want, you can download any of these additional libraries as well. This is a kind of a hand-picked selection of some very well-written and well-maintained libraries which you might find useful for other Teensy projects. You can install them if you want. You can install all of them by clicking this button here. But like I say, the ones that you actually need to install for this project are Audio, Bounce 2 and Time. And then you're ready to install. And once you've installed the TeensyDuino package, you can then load the familiar Arduino IDE as usual, and what you'll notice now in the Tools menu is that you have the option to target Teensy boards. So I'm using a Teensy 4.0, so I'm going to select that as my target board here. And then you can add code in exactly the same way as you would do for any other Arduino project. There's a few changes to be aware of, so what I'll do is as we step through the code, I'll point out any examples where that differs from how you'd normally approach an Arduino project. And in fact, one of those changes comes right at the very beginning, which is in the include section. So as you're probably aware by now, when you include at the top of your code, what you're specifying is external libraries that contain additional functionality that you want to bring into this sketch. And these were the libraries which we included in the installer package. And remember, one thing I mentioned was that you needed to remember the location where you installed the TeensyDuino package to. The reason is because Arduino itself has its own versions of these libraries which are already installed on your computer, and by default they will be looking in your sketchbook location, which is probably something like this. Now the Teensy versions of those libraries, however, get installed to wherever you installed TeensyDuino to. In my case that was here. And to make sure that in this sketch I'm looking at the Teensy versions of this library, what I'm going to do is I'm going to go back into File Preferences and replace that with the directory where I installed TeensyDuino to instead. That's just going to make sure that when we
specified this include statement here, we're using the Teensy versions of these libraries which we just installed, not the generic Arduino ones. Then we go on to the defines. So this is where we specify which pins on the Teensy are to be used for different functions. The 3 pins at the top here, these relate to the SD card functionality which is on the audio shield. So this uses an SPI connection, so we've got a select line, a clock line and a data line to send data to the SD card. If you're using the Teensy Audio Shield as I am, these are kind of hard coded because those are the pins that the board is wired to, so you shouldn't need to change those. If you are using a different type of audio shield, or if you're using a different Teensy, you don't have to slot the board directly onto the shield. You can actually connect them to other pins if you want. If you do that, I recommend keeping the cables as short as possible, but you can, if you prefer to use different pins on the Teensy for those functions, you can do. You just need to change these lines of code here. And then 0 and 1, well, those were the 2 GPIO pins that were left over, not being used for anything else. So we're going to use those to detect when the handset's been lifted. And also, this is the button we're going to wire to play back any messages that are on the SD card. Then we go into globals. So this is where we set our variables that we're going to access throughout the code. And this whole section at the top here, this all relates to defining properties of the audio connections that we're using. So we've got, broadly speaking, what I've defined as inputs, so things that are generating sound. We've got the microphone input itself. This one here is when we are playing recordings back from the card, which are in raw audio format. And then we also have the greeting message, which we saved onto the card, and I'm going to assume you save that in WAV file format instead. And we have also got a synthesizer effect, which we're going to use to generate the tone. So if your message says, please leave your message after the tone, this is going to generate that beep tone at a given frequency and volume. So we've got some inputs. We've then got the outputs. Okay, so where is the final destination of these different sounds going to be? Well, we've got the speaker out, which we're going to connect to the headphone on the handset. We've got a queue, so the queue object is kind of an in-memory buffer, which is what we're going to use to save the recording that's coming through the microphone. And then we've also got a mixer object. So, like I say, the Teensy board is capable of some really quite impressive audio effects. You can use it for guitar pedals and vocal effects like delays and distortions, things like that. And a mixer allows you to combine several inputs into an output, essentially, just as you would do in audio recording equipment. And then we've also got a set of audio connections. So continuing the analogy of a recording studio, these are the cables that are being used to plug the inputs into the various outputs. So we define a patch cord that is going between waveform 1, which was our synthesizer effect, and the first channel of the mixer. We also connect the raw file playback, so the recordings on the SD card, and the wave file playback, which was the greeting message. We define those to the second and third channels on the mixer as well. And then we take the output from the mixer and we send that into the audio output here, which is what's going to go to the speaker output that we listen to on the handset. Meanwhile, we take a separate patch cable and we attach that from the microphone input and we send that to the recording queue so that we're able to stream recording of the microphone input onto the SD card. And then finally we have the overall object at the bottom, which is the audio control chip, which is on the Teensy board. So now I'm a coder, so I'm quite happy kind of writing lines of code like this manually, but one of the things that Teensy actually comes with is a graphical user interface that lets you define this by dragging and dropping items in a GUI. And you'll notice this is actually based on Node-RED. If you've seen any of my other projects, you'll know I'm a huge fan of Node-RED as a way to drag and drop all kind of control interfaces between devices. Well, this is kind of a modified version of Node-RED, which has been used to define
audio connections for Teensy projects. So the code that I've written here, for example, we could have defined an I2S input. You'll see that you get the little graphic appears there that shows you where that corresponds to on the board. So that's our microphone input. And then we've also got the playbacks. We're playing WAV files, and we're also playing raw recordings from the SD card there. We're going to use a mixer, and we're going to also use a synthesizer effect. So all three of these are going to go into the mixer like that. And then we're going to set up a recording queue to take the output from the microphone there. And then we're also going to take an output from the mixer like that. So rather than write lines of code into Arduino like this, what you could do is you could lay out quite a complicated audio setup here, and these lines that are joining the nodes together, those are the equivalent of the patch cables in your audio recording studio. If you want, you can see there's lots of effects we can apply, there's filters, lots and lots of things. It's really worth playing around with this if you're interested in doing audio projects. And once you've laid it all out, what you can do is click the export button at the top here, and it will generate the lines of code that you then need to paste into the top of your sketch over here to define the way that these components are connected. So it's totally up to you. It doesn't write all of the code for you, but what it does is it creates the setup of the audio objects to reflect a particular sort of workflow, as it were. So that's kind of just a really nice feature if you'd like to be able to use that, and that tool's completely free. You can just access it from the link up here. And then we get onto other more regular global variables. So we're going to be saving our recording files onto the SD card. So we create a character array that's going to be the file name that we're saving the recording as, and a file object to actually use the file system in Arduino to save that. We'll define two bounce objects. Now, in some basic Arduino sketches and in some of my previous projects, when you want to detect whether a button has been pressed, you can simply use a digital read on the GPIO pin that the button has been connected to. And that read, if it's a pull-up button, for example, that read will normally read high, and when the button is pressed, it will read low. And that's nice and straightforward. However, when we're using mechanical switches like we are here, particularly when the handset is placed back onto the base, you'll find that there's quite a lot of what we call bounce in that. Those mechanical contacts, as you physically place the handset down, it literally bounces up and down a few times. It makes and breaks a connection in the circuit. And if we were doing a very simple digital read, we'd find a flurry of high and low values that could be misinterpreted as false picking up and replacing the receiver. So the point of using these bounce things here, and this was from the bounce library that we included at the top here, the Teensy bounce library, this is a way of getting effectively cleaner input signals. So rather than just reading the hook pin directly with the digital read, we'll set up a bounce object of it. And the second parameter here says the number of milliseconds to wait until that signal has read a constant value. So basically, when we pick up the handset, what we'd expect is a flutter of highs and lows, but when it has maintained a constant value for 40 milliseconds, that's when we'll say, okay, the handset's definitely been lifted now, or it's definitely been replaced. The button that I'm using to play back messages, well, I'm using a simple, just regular momentary push button for that, so I don't need such a long delay because there's less mechanical noise in that system here. And then we define an enumeration of different modes that the telephone can be in. So this is a simple state machine, and I've used state machines in other projects involving telephones in the past. It's quite an interesting exercise to think about appliances in your house that you use every day and think about the different states they can be in, because when you come to write the code, you sometimes want them to respond differently to a button input, let's say, depending on what they're currently doing. If you're currently recording a message and you place the handset down, well, we need to close the recording, save the file, increment the counter to the next file, things like that. If you are
If you've already recorded your message, or if you're hearing the greeting, perhaps it will do something else. So we define the possible states that the telephone can be in. So initializing is when it first turns on. Ready is when the phone is effectively not doing anything. It's ready to be picked up, but the handset is currently on the base unit. Prompting, that's when the handset has been picked up and the person is holding it to their ear and they're hearing your message back telling them what to do. So we're not recording at that point, we are playing back through the earpiece, but the handset is off the hook. Then we move on to the recording stage, and then playing is when we've pressed the button to play back the messages on the card. And from each of those states there, if the handset is replaced, then we go back to the ready state. But we start off in the initializing state, so that's the first thing that happens when we first start the code off. And we enter the setup function, so setup runs when power is first received. And what I would normally do at the start of a setup function is begin a serial connection and then output the name of the file and the version number to the serial monitor. Now, with Teensy boards, one of the slight differences that I mentioned from Arduino is that you don't need to call serial.begin, and you don't need to specify a particular speed that you're connecting at here, because by default Teensy boards always initialize serial communication anyway when they start up at full USB speed. So we don't need that line here, but I've kind of left it in and commented it out just to remind myself that when I look at this code in the future, I'll go, hang on, there's a bug here, there's no serial begin. Well, no, because we're targeting the Teensy board up here, and that doesn't need serial.begin. We then configure the input bins. I'm using pull-ups for both of them, so we'd expect them to have a high value, and then they go low when they are connected. We initialize a block of memory, which we're going to use to store the audio. So as we stream audio from the microphone, we're going to save it to the SD card kind of in byte chunks of 512 bytes at a time. So we need a little block of memory to hold data in before we stream it to the SD card. I've set a value of 60 here, which was sort of the default which I've seen used in other Teensy Audio examples. Seems to work perfectly well for this example. If you find, let's say you have a very slow SD card. SD cards come in different qualities and different write speeds. I'm using a relatively fast one. I think it's a grade 10 or something. But if your SD card is slow to commit data to the card, you might need to increase the memory value here just to make sure that you get you don't drop any data, kind of basically. But that's a value which, like I say, seemed to be the default value, and I haven't had need to change it, so I've just left it like that. We actually begin the audio shield. We specify which input we're using, because there's a couple of different inputs. We're using a mic input. Another alternative value we could specify there was for a line input, which would obviously change the pre-amplification levels and things like that, but we're using the mic input here. And we specify an initial volume for the output as well that we're going to be sending to the speaker. Some of these things are things that you will need to change empirically. You know, if you're getting distortion at the top end of the speaker in your handset, you might want to reduce that value, but that worked for me, just setting it to half. And we'll just play a little kind of chime sound effect when we first turn it on to give some kind of feedback that the system is online. I don't have a display of any kind on the handset. I suppose I could have installed an OLED display on the unit just to give some readout. And I'm not anticipating having a computer out in the field when I'm using this, so I need to have some kind of other feedback to let me know what state the machine is in. And the most obvious one was to get it to play a little bleep when it kind of correctly powers on. So we're going to call some functions on the waveform object, which we declared up here. So remember this waveform, we have connected a patch cable to it, which is taking it to the mixer. And then we've connected a patch cable from the output of the mixer to the audio output. So anything we now
applied to the waveform object is going to end up going through those patch levels and coming out the output to the speaker. So we'll begin a simple sine wave at a frequency of 440, so concert A, at an amplitude of 0.9, and we'll wait for 250 milliseconds, so quarter of a second, and then we will set the amplitude to 0 again, so turn it off, and then we'll just wait a little bit before carrying on. So we'll basically have a quarter of a second beep at concert A, and then we'll stop. And you can have lots of different status effects that you want to communicate through different audio effects. You could have like a chirp upwards or a sad trombone sound effect if something had gone wrong, something like that. But a single beep just lets me know it's come online. Then we initialize the SD card. Obviously you'll need to have an SD card inserted into the slot to be able to initialize it successfully. We just specify what the Mozzie and clock pin we are using. On Arduino boards, you're kind of tied to having a particular Mozzie pin and clock pin because of the way the hardware is wired. On Teensy you can select different pins, as I mentioned at the top, but if you're slotting it directly into the audio shield, then you want to be using the pins that are defined up here. So we begin the SPI connection, which is going to be used the SD card, and we just check that we can actually initialize that successfully, otherwise we'll print a message to the serial slot. I've assigned a little bit of gain to the microphone. Again, much like the output level, which I defined in the volume line here, you'll have to set this a little bit through trial and error. So this is actually measured in decibels. So I'm applying a gain of 15 decibels to the input from the microphone. Again, if you listen to the sound playback on the recordings and you notice that you're getting the frequencies cut off at the top end if the volume's too loud, you can reduce that. Or if it's too quiet, you can increase it, obviously. Now the next two functions here, these relate to the fact that when we save files on the SD card, we want them to be time-stamped. That's a useful way. We're going to increment the number anyway, so we'll know it's recording 1, recording 2, recording 3, but it would also be useful to know the time at which those recordings were made. So that is what these two lines here do. The first one sets what's called the sync provider. So that's to say that the real-time clock interface that's on the Teensy, we're going to use that to create a time object, or to provide the time, to the time object. And then this is a callback that's used for the file system to say every time an event takes place on the file system, so if a file is created or if it's modified, saved, whatever, after that happens we're going to specify a callback that's going to provide the right date and time for that file system function, and that callback is going to reference the time that was provided up here. So don't worry too much about this, and actually it's not essential at all anyway. If you don't have a real-time clock on your board, it's not going to be the end of the world anyway. You'll just get a default timestamp attached to each file, and you'll still be able to separate them out anyway because I have different file names. But I just thought that was a kind of a useful feature to have, so that's why I included it here. And finally, once we've got to the end of the setup function, which we're currently in, we can change the mode. We were initializing, and now we are ready because we are done with the setup. And that brings us on to loop. So the loop function runs over and over again continuously for as long as the program is running. And what it does on every iteration of that loop, well, the first thing it does is to check any inputs. So these are both called button, but remember that the button play really is the button. That's the button you can press on the back of the phone to listen back to messages. The one I've called button record, I think of like a button because I'm using it as one, but it's actually the switch that detects whether the handset has been replaced. So we are not going to act on those inputs yet, but we're just going to call the update function, which will take note if their values have changed at all, based on the bounce settings that we defined at the top here. Okay, so that's what we're going to update the bounce objects, which we're going to be able to then reference a little bit later on in the code. And then what we do next depends on the mode that the telephone is in. So the first mode we could be in, well, we could be in the ready mode. So we've completed the initialization. We're just waiting for some input. And the two things that can happen here are we might detect a rising edge of the record button. So if that's the case, what that means is that the handset has been lifted up and we want to move on to the next mode, which is to play the prompt for the user to leave their message. Or we could detect a falling edge of the play button, and if that's the case, we want to play through all recordings. So this idea of the rising edge and the falling edge, this is when a variable that was previously low changes to high, and this one is when a variable that was previously high changes to low. And when I showed the two telephone handsets earlier, we had the more modern digital style handset and we had the older kind of analog style handset. Remember I pointed out that the button switch acted in the reverse direction on both of those. One of those, there was a continuous continuity between the two button pins, and then that was broken when the handset was placed, and the other one, it was not normally connected and then it became connected when the handset was broken. And if you find that your handset behaves the opposite way round to the one that I'm using, this is what you need to change here. You need to change whether you're listening to a rising edge or whether you're listening to a falling edge. So it's very straightforward. You can literally overwrite this with the correct behavior. So the difference is whether you're listening to something going low to high or something going high to low. And those are the two actions that we want to do based on those inputs. Now, if we were ready and the handset has been lifted, then we go on to the prompting state instead, which is what we have in this bit here. So what we're going to do here is we're going to wait a second to start with, because if the handset's just been lifted and we start playing the greeting straight away, we'll actually not give the user the chance to hear the message yet. We need to let them lift the handset up to their ear. I've waited a second for that. Possibly could do with being slightly more generous than that, I guess. But I wanted to make sure I wasn't waiting too long so that they actually start leaving their message without having heard the greeting. Again, change that to fit your particular scenario. And then we're going to play the greeting to them. So this is a message which I'm assuming you've saved on your PC or on your phone perhaps, and you've saved it onto the SD card. It's a WAV file, and we're going to play it using the play WAV1 object. And then just to go back to this again, remember that play WAV1 was one of the objects that was feeding into the mixer via the patch cord, and then the mixer was being fed into the audio output. So this is how we're going to play a WAV file through the speaker in the handset to the user. We're going to just call the name of the file. If you've named your file something different on the SD card, obviously you just supply a different file name. And then while that greeting is playing, because I don't know how long the greeting message is going to be, so we're going to just continue the loop here while it's still playing. We want to check that the user has actually listened to the end of the message without replacing the handset. So we're going to continue calling the update function here while the message is playing, just to listen for that button record. And if the button record has a falling edge, so this is where it can get a bit tricky to keep track of the falling and the rising edges, but falling edge here, it means that the handset has been replaced while they were still listening to the greeting message. Well, in that case, we'll stop the message playing anymore and we'll go back to the ready state. So that's someone who's lifted the handset up, heard you saying, "Hi, this is Alistair, please leave a message," and they go, "Oh no, actually, changed my mind, I don't want to leave the message, I'm going to put the handset back." So this kind of cancels the operation, I guess. That's the way of thinking about this. However, if that doesn't happen, so we've got to the end of this while loop how we've played the whole of the message, then we move on to this section here instead. So we'll now just put a little debug message to say we've started recording what they're saying, and we'll play the tone at them. So remember, this is the leave your message after the tone. This is the tone. And then we will start the recording function. So start recording. We'll get to start recording in a moment, because start recording here is a little bit more heavy on the technical details about how we access the SD card and things like that. So we'll come to that in a second. But just know for now that what that does is advance the main state into the recording mode. So if we now take a look at that, that is from here to here. So what do we do while the phone is recording? One of the possibilities is that the user gets to the end of their message, and if that's the case, what they do is they replace the handset, and once again we have a falling edge on the record button in that case. Just as we had a falling edge on the record button we were listening to here when they replaced the handset hearing the greeting, well, this is when they replace the handset after they were recording. And what we do then is we call the stop recording function. That's going to tidy up the saving of the audio onto the SD card. And we'll also just play another little tone just to say that the recording's been finished. This time, notice that I'm calling a different frequency. So this is a C above the A, so it's a higher pitched tone. And we'll just do a double beep this time. So we're going to play a high note, a high C, for relatively loud for 50 milliseconds, and then turn it off for 50 milliseconds, and then we're going to repeat that play again. So it's a little high beep beep, just to let the message has been finished. Otherwise, so this else here, this is if we're in the recording mode at the moment and we don't hear a falling edge of the recording. Well, that just means that they're still recording their message, and if that's the case, we're going to continue recording. And finally, we could be in the playback state, and there's nothing particular special we need to listen to in the playback state. That is handled by the play or recordings function, which is down here. So that's it for the loop function itself. Those are, we basically listen to the two buttons, and then we behave differently depending on the state that the telephone is in. But we did call some functions there, so now we're going to go and look what those functions do. And there are three functions related to the recording of the audio from the microphone. There's start recording, there's continue recording, and there's stop recording. And they were all called at different points in the loop function up here. So we look at start recording to start with. Well, what are the actions that we want to take when the user has first started a new recording? Well, the first thing we want to do is we need to choose the new file name that we're going to save this recording as. So what this function here does, I'm going to count from 0 up to 9,999. I'm assuming you're never going to want to have more than 10,000 messages on an SD card. I suspect at that point the file system will probably throw a wobbly anyway. I mean, in theory you can increase that number if you want, but there you go. And what we're going to do is we're going to form a new file name based on that counter that we've reached to, appended to just .raw at the end. So this little format here, this is a useful thing to get there. This % format here says that I want to create a string that's going to be the name of a file. It's going to be formed from a number, and I want that number to have 5 places in it that are padded with zeros at the beginning, and then I want to have .raw at the end of it. So what this will do on the first iteration through this loop, what this will do is this will set the value of file name to be equal to 1.2.3.4.1.raw. Okay, that's what this line here will do when I is that's what it will do when I is 0, which is the first iteration of the loop. Then it will go 1, then it will go 2. And obviously when we get into double figures, it will just pad it up to 5 places like that. So this is going to set the value of file name to something like this. And then what we need to do is, well, have we already got a file 12 already? And to do that, we call the exists function, not the SD object, and we'll check whether that file exists or not. If it doesn't exist, then that's fine. We found the first file that we're allowed to use and we can carry on. If that file does exist, well, in that case we need to continue the loop and move on to the next one. So this should find the first file number that doesn't already exist on the SD card. Essentially, that's what this does. And once we've found that file, what we do is we open it. So we call the open function the SD object, and we assign that to the frec file object. That was a global variable that we defined at the top up here. So now we've opened the file, we're able to call that object to save files, save data to it. Sorry. We'll just put a little debug message here, and we will begin the recording queue that was the audio object on the Teensy, and we'll set it to mode recording. Otherwise, if that fails to open the file, then we'll just put a debug object here. So the important thing we've done, we've decided a file name that we can use, we've opened that file ready for recording, and then we have begun the recording queue up here. Okay, that's the main things of start recording. Now continue recording. Well, what we do for as long as we call loop in, every time loop is called and we are recording, what we need to do is to save to the SD card, to stream as we go any audio data that has been received in that queue there. So that's exactly what we do here. We check that there is some data available, and if there is, we create an array of bytes, 512 bytes, and what we do is we copy them. First of all, we read the buffer that is available on the recording queue into this buffer that we just created here. And then what we do is we write from that buffer to the frec file which is on the SD card. Now, this, like I mentioned before, the speed at which this write happens varies depending on the brand and the quality of the SD card you're using. I recommend using a good quality, highly rated SD card with a fast data transfer rate, because that will ensure that this operation happens quite quickly and that you don't exceed the buffer size of your audio. So it is worth investing in a decent quality. I use SanDisk Ultra SD cards for this, and they've worked pretty reliably for me, if you want a particular recommendation of a brand there. And we do that in every iteration of the loop in which we are still recording. We read that buffer into an array here, and then we write that buffer to the file on the SD card. And then we stop recording when the handset is replaced. And at that point, we can kind of tidy up after ourselves, basically. So we can end the recording queue. We don't need to add any more data onto it. And we just need to flush out, if there is kind of like a partial amount of data that had been written in the last frame, well, we need to catch that onto the end of the file as well. So for as long as there continues to be any data available, we are going to write that onto the end of the recording file, just as we were up here. We're just going to write to the end of the buffer to that file here. Then we can close the file object and we return to the ready state. And that's the three functions that are related to recording. So we start recording, we continue recording, and then we stop the recording as well. Now we have the function that is called when the button is pressed to play any recordings that are saved on the file. So this was called on line 141 here. So this is when the phone is ready and we pressed the button. And what do we do here? Well, the first thing we need to do is we need to actually sort of enumerate all of the recordings that are saved on the SD card. So we open the root directory on the SD card. If you want to, you could place these into a subfolder. If you do that, you obviously need to change the folder name that's here, and you also need to change the place where they are saved to here as well. So you'll need to specify not just the file name but also the folder that it is contained in there. But to be honest, there's no reason not to just save it in the root of the SD card anyway. If you place it in a subfolder, you're just adding more complexity to the folder structure for no real benefit. So we open the SD card, and then what we do is we look through all of the files that we find. So that's what this open next file function does here. It's kind of iterate through them one at a time and assign them to a file which we call entry. If this command here returns false, which is what happens here, that means we've got to the last file in the directory, and then we can break out of this function and just close it. If we have found a file there, what we're going to need is we're going to play it using our raw player, because that's the format that we're saving the audio in, as a raw audio file. So we're going to just check that the file that we found is indeed an audio recording, because remember we did have one file saved on our SD card which is a WAV file, which is our greeting file. There might be other stuff saved on your SD card as well. I mean, I'd recommend you start with a clean SD card, but just to make sure that we're not going to try and play, you know, some kind of photo that was saved via your digital camera on this SD card or something like that, we're just going to check that the file we've looped over here is actually got the raw extension on it. So that's what str does. It lets you compare two string values, and we're going to take the last part of the file name, which is going to be the extension. So we're going to take the final 4 characters of the file name. We're going to compare that to see whether it's equal to .raw, and if it is, we know we're looking at a raw audio file, which means that we can play a little beep just to say, okay, we found a file, play a beep, and then we are going to pass that file name to the play raw function. Okay, and then we're going to change the mode to mode.playing. Once we've done that, we can close the file itself, because the only reason we needed that was to enumerate through the files and to get the file name of each object to pass to the play raw function. So we can now close the file. We've got to make sure that we sort of tidy up ourselves. So, you know, having looped all these directories, opened all these files, played them, let's make sure that we actually close them at the end as well. And a little bit like while we were playing the greeting message at the beginning, we're going to do the same thing here. While we are playing back one of the messages on the SD card, we still want to continue to listen to any possible updates or any inputs. And I mean, the logic I've applied here is slightly different. What I've said is if you're listening back messages at the moment, and either you press the playback button again, which is a rising edge on the playback button, or if you put the handset down, which is a falling edge on the record button, if either of those two events happen, then we're going to stop playing back any recordings and we're going to return to the ready state. Again, if you want to customize this logic in different ways, maybe you want to actually have separate buttons on the back. Maybe you want to have a button that you know, advances to the next file to play back, and you could actually kind of, you know, loop through them manually, as it were. Then you could add that in absolutely in this function here. But what I'm doing is, at the moment, I think the simplest thing, which is to simply loop through all of them and play them back, and then stop when either of those two events happen. We're nearly there. So right at the end of the code, just a couple more helper functions. The first one was that sync provider for the clock, which I mentioned at the beginning. So this returns the current timestamp from the real-time clock chip on the Teensy. And then this was the callback for the file system that's going to provide the date time that will allow the timestamp to be correctly assigned to any recordings that we make. So you don't need to worry too much about that. And finally, you'll have noticed a few times in the code I called a wait function here. Now you might be familiar with a delay function, which is more commonly seen in Arduino codes. Delay literally pauses execution of the entire code at that point and then doesn't carry on to the next line until that number of milliseconds has elapsed. And sometimes that's absolutely fine, and sometimes that's the behavior you want, but it does, by definition, make the code completely unresponsive for that duration of time. Literally nothing happens at all when you call delay. And if you've got any kind of system that depends on input that could arrive at any point, that input is not going to be detected when you're delaying the code either. So wait is a custom kind of alternative to delay, if you want, which I've implemented at the bottom here. And what that's going to do is it's still going to wait until a certain amount of time has passed, but it's going to continue to update the record and the play buttons in that time while it's listening. The other thing to mention is that it does make use of the Teensy instruction here called elapsed millis. Normally Arduino has something called millis which you'd use, but Teensy has elapsed millis, which is a kind of a static object which you can get in a function that will tell you how many milliseconds have elapsed since the code first began executing. Yeah, and that's it. So I've shown you how to build and code your audio guestbook. Now imagine you've used it a few times and you've got some recorded messages saved on the SD card. Now I just want to explain a little bit about how you go about retrieving those messages. So they're saved in raw audio data format. So as you saw in the code I just showed you, what that means is that the microphone data is streamed as a continuous series of bytes onto the SD card. There's no kind of file compression or metadata or header to the file info, anything like that at all. So if you're using a PC, I recommend using Audacity to load a file like that. It's a great open source software and it gives you the option to import raw data here. So if I select one of the files from the SD card there, now because the file doesn't have any metadata associated with it, we need to explicitly say the format in which those bytes were saved in. And the format you need to choose is signed 16-bit PCM, it's little endian, it's a mono recording because obviously only recording from a single microphone in the handset of the telephone, and it is at 44.1 kilohertz audio rate. And then you can click the import button here and it will bring your audio file into Audacity, and from here you can play it.
And then it automatically starts recording everything said into the microphone.
And you can also export it, you can save it as an MP3 file, you can do whatever you want with it. But to do that for every individual file on an SD card, let's say you've got hundreds of recordings, there's a little bit of a clunky process to have to load them individually like that. So what you might prefer to do instead is to batch convert all of those raw audio files into a more common format like WAV or MP3 instead. And to do that, I would recommend you use a program called SOX. So you can download SOX from sourceforge.net/projects/SOX. Again, it's an open source program and it can convert audio files between lots and lots of different formats. Now it runs as a command line, which means it doesn't have a nice graphical interface, but it does mean it's very good for batch conversion of a whole directory of files, let's say. So here is an example of how you could write a script using SOX to convert all of the raw files on an SD card saved from the guestbook. So what this does is it says for all files in the current directory that have the raw extension, so you call the SOX executable, which you download from here, and you specify, just as I just did in Audacity, what the file format of the incoming data is. So it is 16-bit, it's got a single channel, and it is at 44.1 kilohertz audio recording, and it is a signed integer. And then what we're going to do is we're going to take each input file that we find in this directory and save it as a WAV file instead. And because we've assigned the extension onto the output file here, SOX will automatically recognize, you want to create a WAV file, and will apply all of the settings. Then you'll have something that is a more common format that you might find easier to load. If you want, you can convert them to an MP3 file instead. To do that, you just need to install the lame MP3 encoder as well. But there's instructions on how to do that in the SOX documentation. So I just wanted to mention that as well.
So that brings me to the end of this tutorial. If you're hosting a wedding reception or a party in the near future, I think an audio guestbook is a really fun idea of an interactive way that you can get your guests to leave you with memories of the day that you can treasure for the future. And by making it yourself, you're able to customize the exact way that the handset looks and feels and fits it with any theme that you might have.
If you've got any questions or comments, then please do write them below and I'll do my best to answer them. Or if you've got any ideas for other projects that might use the same hardware, that Teensy audio board and the ability to record high quality audio, I'd love to hear your ideas and maybe I'll incorporate them in future videos. I'll post a link in the description below where you can download the code and the wiring diagram that I've used here as well. And I want to say thank you very much to all my Patreon supporters who facilitate me and enable me to create these kind of tutorials and host them here on YouTube. I really do appreciate your support, so thank you very much. Other than that, just want to say thanks very much for watching and I look forward to seeing you next time. Okay, cheers, bye.